Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
The discovery also holds interesting possibilities for cooling devices and processes in industrial applications using only the basic properties of water. Their work was published on January 21 in the journal Physical Review Fluids. Water can exist in three phases: a frozen solid, a liquid, and a gas. When heat is applied to a frozen solid, it becomes a liquid. When applied to the liquid, it becomes vapor. This elementary principle is familiar to anyone who has observed a glass of iced tea on a hot day, or boiled a pot of water to make spaghetti. When the heat source is hot enough, the water's behavior changes dramatically. According to Boreyko, a water droplet deposited onto an aluminum plate heated to 150 degrees Celsius, 302 degrees Fahrenheit, or above will no longer boil. Instead, the vapor that forms when the droplet approaches the surface will become trapped beneath the droplet, creating a cushion that prevents the liquid from making direct contact with the surface. There are so many papers out there about levitating liquid, we wanted to ask the question about levitating ice, said Boreyko. It started as a curiosity project. What drove our research was the question of whether or not it was possible to have a three-phase Leidenfrost effect with solid, liquid, and vapor. Going into the ice curiosity sparked the first investigation in Boreyko's lab some 5 years ago in the form of a research project by then undergraduate. What he observed was fascinating. Even when the aluminum was heated above 150 C, the ice did not levitate on vapor as liquid does. Kusumano continued raising the temperature, observing the behavior of the ice as the heat increased. What he found was that the threshold for levitation was dramatically higher, 550 C, 1022 F, rather than 150 C. Up until that threshold, the meltwater beneath the ice continued to boil in direct contact with the surface, rather than exhibit the Leidenfrost effect. Boiling water is optimally transporting heat away from the substrate, which is why you feel ample heat rising from a pot of water that is boiling, but not from a pot of water that is merely hot. This means that the difficulty in levitating ice is actually a good thing, as the larger temperature window for boiling will result in better heat transfer compared to using a liquid alone. It is much harder to levitate the ice than it was to levitate the water droplet, said Boreyko. Heat transfer plummets as soon as levitation begins, because when liquid levitates, it doesn't boil anymore. It's floating over the surface rather than touching, and touching is what causes it to boil the heat away. So, for heat transfer, levitation is terrible. Boiling is incredible. Using ice for heat transfer as the team explored possibilities for practical application, they looked to their existing work. It requires a substance or mechanism that can move energy away from a hot surface, redistributing heat quickly to reduce the wear and tear on metal parts. In nuclear power plants, the application of ice to induce rapid cooling could become an easily deployed emergency measure if power fails, or a regular practice for servicing power plant parts. There are also potential applications for metallurgy. To produce alloys, it is necessary to quench the heat from metals that have been shaped in a narrow window of time, making the metal stronger and less brittle. If ice were applied, it would allow heat to be offloaded rapidly through the three water phases, quickly cooling the metal. Boreyko also foresees a potential for applications in firefighting. You could imagine having a specially made hose that is spraying ice chips as opposed to a jet of water, he said. This is not science fiction. I visited an aerospace company that has an icing tunnel, and they already have this technology where a nozzle sprays out ice particles as opposed to water droplets. With myriad possibilities, Boreyko and Edalatpour are excited about the new contribution that has come to the science world. Looking back over the past 5 years, they still credit this exciting development to their shared spark of curiosity and the drive to be creative in research. Materials provided by Virginia Tech. Original written by Alex Parrish. Note: content may be edited for style and length. Mojtaba Edalatpour, Daniel T. Kusumano, Saurabh Nath, Jonathan B. Boreyko. Three-phase Leidenfrost effect. Physical Review Fluids, 2022, 7, 1, doi, 10. 1103, Phys Rev Fluids. 7. 014004 Virginia Tech. Using ice to boil water, researcher makes heat transfer discovery that expands on 18th-century principle. Science Daily. https://ift. TT, 35ID1F7, accessed January 21, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.